Take the blue pill. End poverty, solve world hunger, and attain world peace. Take the red pill, and you
gain the ability to understand quantum physics entirely.
Alright, now, imagine that you have to choose between the red or blue pill. But these pills are magic pills. They can change color. But when I reveal one, the other immediately change to the opposite color. So these pills are connected in some magical way, and in quantum physics, this phenomenon is called entanglement. In classical physics, different rules and laws govern the physical world around us. However, classical mechanics break down at smaller scale. Really small objects, like atoms, do not follow the same laws of physics. All elementary particles have intrinsic spins associated with them. However, it is important to note that the particles is not actually spinning, but rather is an analogy represents its angular momentum and its orientation in space. When measuring the spin, a particle can either spin up or spin down. But if we choose to measure horizontally instead, the particle will have a 50% chance of being spin up and 50% chance of being spin down. The act of measuring initiates an interaction and can actually change its original quantum state. Now, if we choose to measure at 60 degrees, it will spin up 3/4 of the time and spin down 1/4 of the time. When particles interact with each other, they can form a special connection called entanglement. Their quantum states become correlated in such a way that changes in one particle could have effect on the other. Measurements of physical properties, such as spin, can be found to be perfectly correlated to one another, such that the pair's total spin is 0. This connection persists no matter the distance between them, as long as they remain entangled. When two particles are entangled, it doesn't matter at which angle the detectors are set, or how far apart they always measure opposite spin. This idea of an event at one point in the universe could instantaneously affect another, even arbitrarily far away, just doesn't sit well with Einstein. He preferred an alternate explanation, that these particles might have some hidden information within them, that they agree upon which spin they would show if measured. Some scientists accepted this explanation that the spin of the particles are predetermined, but the information is just hidden. Later, however, John Bell came up with a way to test this hypothesis. The setups include two sets of detectors. Each can measure in one of three directions, randomly and independently of each other. Now, let's stick with Einstein's assumption that there is hidden information, and we can think of this as the particle's secret plan. One plan can be that the first particle gives spin up for all three directions, and the other particles give spin down for all three directions. Another plan, or plan B, can be that the first particles give spin up, and the other particles give spin down, respectively. All other combinations are mathematically identical, so we will only analyze these two plans. So, for plan A, we can easily see that the detectors would give opposite measurements 100% of the time. For plan B, however, they only give opposite measurements 5 out of 9 times, and these are all the possible combinations. So, combining the two plans, this experiment should give opposite measurements more than 5 out of 9 times. However, the experimental results were only 50%, inconsistent with Einstein's assumptions. So, how can quantum mechanics account for this result? Let's say the first detector gives spin up for the first direction, as the particles are entangled. The second detector, if measured in the same direction, would give spin down. However, if measured in the other two directions, it will give spin up 3/4 of the time, as it makes 60 degrees with the original state. So, 2 out of 3 directions give spin up 3 out of 4 times, equating to 50% probability of both detectors giving the same measurements, which is exactly what we see in this experiment. So, quantum mechanics works. Entangled particles exhibit a connection that seems to operate faster than the speed of light, influencing each other's state instantaneously. Does this mean we can achieve faster than light communication? Well, everyone agrees that the answer is no. That is because the result you find at either detectors are random. Both sets of data would be random, just the opposite random of the other. Quantum mechanics might not allow faster than light communication, but at the very least, it will make Einstein happy as it doesn't violate the theory of relativity.